All right, guys, welcome to Unit 4. This one's on magnetism. So we're going to study first the anchor phenomenon. What would happen if the Earth is hit by a massive solar storm? If you don't know what a solar storm is, it's basically the electromagnetic radiation given off from the sun via the nuclear fusion process. It basically emits a bunch of electromagnetic radiation particles towards everything within its distance in the solar system. So it really hits the Earth. What would happen if the Earth was hit by one of those, but a massive one? Think about it. How could radiation affect anything that operates on electricity? How would it affect your body? What do you know about radiation? Well, if you guessed that it wouldn't be very good, you'd be right. At least a massive solar storm. None of those events are on the horizon that I know of. But we do get hit by solar wind quite often, and you might recognize this. Let me ask you this: what does this picture mean to you? Well, if you said, "Oh, it's the Northern Lights" or Aurora Borealis, you'd be right. And this actually occurs because of solar wind. So you see, when the solar wind from the sun hits the magnetosphere of the Earth, it actually causes a disturbance within the particles in that magnetosphere. And that creates this light show that we know as the Northern Lights. And it occurs everywhere in the magnetosphere, but it's mainly visible within the concentrated areas within the poles of the Earth, so the North and the South Pole. And this is a good illustration of what it looks like in a very animated scale. Obviously, the sun and the Earth are not this close together. You would never get a picture of them. But basically, the particles travel towards the Earth, but they are deflected by the Earth's magnetic field. I bet you didn't know this, but the Earth is actually a giant magnet. That's right. William Gilbert discovered that the Earth is actually a large magnet with a north and a south pole, but not the north and the south pole that you know of, the one with Santa Claus and the one with all the penguins, but actually in the north and south magnetic poles. So we have the north and south geographic pole, but don't get that confused with the north and south magnetic pole, because it's actually opposites. Our magnet is actually flipped upside down. So the north geographic pole is actually the southern magnetic pole, while the south geographic pole is actually the north magnetic pole. So it's actually flip-flopped. Our magnet is quite literally upside down. And that's very important, because if you use a compass, if you were using it correctly, you would see that the north arrow, or the northern part of the compass, is actually attracted to the north magnetic pole. But the reason why it's attracted it's attracted to the north geographic pole. But the reason why it's attracted to the north geographic pole is because that's actually the southern magnetic pole, because it's an opposite charge, and we know that opposite charges attract. So north and south magnets attract, while south and south magnets would repel. So you have to orient magnets the right way. And there's a reason for this. Magnetism is actually caused by the motion of electric charge. And that motion, like any other motion, has a direction, it has a vector. And that's very important when you are looking at the directions or the orientation of the domains of the unpaired electrons. So a good way I illustrate this with my students in my class is I have everyone stand up and I say, okay, we're all random, right? There's no magnet here. But then all of a sudden, everyone turns and faces a specific item in the room. And that's what it looks like in a magnetic material. All those unpaired electrons, those domains, all line up and they face the same direction. And that's the orientation of the magnet. And that's why we have north and south poles. It's because the current is flowing in a specific direction. And that's very important to the magnetic field around that object, and also the magnetic forces in the direction that they are orienting in, because we know that all vector measurements have a direction, and magnetic forces have direction, as does current and magnetic fields. So what is the difference between electric and magnetic fields? You see, in 17th century, scientists actually observed that electricity could create magnetism, and the magnetism could create electricity. And they were like, how are these related? Well, they actually operate on the same principle of electromagnetism. And we're going to look at that in a minute. But basically, electric fields is having charged particles, and charged particles have a linear direction that they travel in based on what they're attracted to. Negatively charged particles and positively charged particles. They're always going to move in a specific direction, and that direction is not circular. It's in a linear direction. Now, magnetic fields is actually created outside of that current, and that stems from the motion of those charged particles. You can't have magnetism without motion of electrically charged particles, but you can have electric fields without motion, and we call that electrostatic forces or electrostatic fields. Now, electromagnetism, let's go back to that. So I already told you that whenever current travels through a conductor in a straight line, magnetic field is created on the outside of that. And that's a discovery from James Maxwell. James Maxwell discovered electromagnetic radiation, and specifically light. And he noticed that both magnetic fields and electric fields travel through space at the same rate as light. And that's because they are composed of electromagnetic radiation, which is just essentially traveling electrons, excited electrons. And they produce a force, both of those produce a force called electromagnetic force. Now, the last thing I want to introduce to you before we start getting into dipoles and before we start getting into magnetic field lines is Fleming's right-hand rule. Now, we're going to get into current, field, and force, but it's important we remember this. And this is a really easy way to remember how these things travel. So the first thing you're going to do is you're going to assign a direction of current. And it really isn't important which finger you use for which, but it's important that they operate in a three-dimensional plane. So if current is going up, that means electrons are moving up. So imagine this is a wire, a conductor in the wall, a copper wire that electrons are going to travel through to get to an outlet or a switch or something like that. Current is traveling this way. The magnetic field is actually going to be casted outside of that. So it is moving perpendicular to that current. And perpendicular to both current and field is going to be the electromagnetic force. So I'm going to do this way, but current, field, and force. So force would be pointing towards you. Okay? So three-dimensional plane. The force is going to be pushed or pulled this way. The current is flowing this way, while the magnetic field is this way. So what you would see current traveling in a straight line here, the field being formed on the outside of it, and a force being applied on a third plane. So that's the last thing I'm going to leave with you today. We're going to get into this later on, but this is a good introduction to magnetism, and the most important way we can look at it is what's keeping us here on the Earth right now, and that's the Earth's magnetic field. It's protecting us from the sun. So until next time, guys.